What is up, AP Physics 1 students? We are here with our fourth edition of this Cliff Note review session, and today we're going to be talking about impulse and momentum. And we just finished talking about energy, and one of the big things with energy is that energy is always conserved. Well, guess what? Impulse and momentum is always conserved. So when do we want to use momentum versus using conservation of energy? And the answer is anytime that we have two objects interacting with each other in terms of a collision, we want to utilize conservation of momentum. So conservation of energy we want to use if we have an initial point and a final point and some energy has changed. Conservation of momentum we really want to use anytime we have two objects colliding or interacting. So we're going to quickly go through that right now. So in the last section, I talked about the work energy theorem, and work is where energy comes from, right? And work is force times distance. Well, similarly, we have a different concept, and that is that impulse, which we use the letter J, is where momentum comes from, which we use the letter P. And J is, instead of force exerted over a distance, it's a force exerted over a time interval. And if you recall, there's a really long list of stuff that we can talk about. So first off, we could get a graph. If I were to make a graph of force versus time, that similarly to force versus displacement, the area under the curve of that graph is going to be my impulse. So that kind of makes a long list of our impulse momentum theorem, which we'll talk about in just a second. So this is a triangular graph. Now, it doesn't have to be a triangular graph, but we use this to talk about this concept of the maximum force exerted and then the average force exerted. And it's a little confusing because we want to make sure that if we're using the area under the curve, yeah, we can do it that way, or we're going to replace this graph with a new graph of force versus time, and then we'll use F average to approximate that curve. Oops, I did that wrong. Average to approximate that curve. So there's a few different ways of doing that, but that leads me to this concept of the impulse momentum theorem. And the impulse momentum theorem tells us that the impulse delivered to an object is equal to the average force exerted on that object over time. So if I hit a ball, the average force, and that again comes from the graph F average, F where we graph F average versus time. That's the average force exerted over time, and that causes the object to change its momentum. Now, momentum, if you recall, is a very simple quantity. It is a vector quantity. Direction does matter, unlike energy, and that is mass times velocity. So it's equal to our change in momentum, which is also our final momentum minus our initial momentum, which is also our mass times our change in velocity. So all of these things are true. This is the impulse momentum theorem. When I have an impulse delivered to an object, it changes the object's momentum. Momentum is a vector quantity. It has mass and velocity, so direction does matter. And that's really about it. But we could also say that this impulse is the area under the curve of the force versus time graph. And that adds one more little thing of into that. So we can use, if you see a force versus time graph, we know that it's impulse. If we see a force versus displacement graph, we know that it is conservation of energy. So a couple quick things there. Now, a nice little thing is to talk about where does this come from. So where impulse and momentum comes from is that we know forces cause acceleration. So force equals mass times acceleration. Well, acceleration is actually a change in velocity over time, which means that my force equals mass times delta V over delta T, and then I get F delta T equals m delta v. So that is my impulse momentum theorem actually right there. That is how, or that is where momentum comes from. So momentum, again, anytime I change the way I'm analyzing something, it doesn't change what my result should be. It's just telling me a different way, or a different way of relating some concepts. So anytime that we have a force exerted over time, that will give us a change in velocity for a mass. So how did we utilize this? Well, once again, we use this to talk about collisions. And I reviewed this in the last video, but elastic collision is a bounce collision. And if a collision is elastic, perfectly elastic, I talked about this a lot in the last video, a perfectly elastic collision, energy is conserved, energy is always conserved, but also this concept of mechanical energy is conserved. And mechanical energy is usable energy. It's the sum of potential and kinetic. We have inelastic collisions, and those are hit and stick. And in a hit and stick collision, mechanical energy is not conserved. So I can't use the conservation of energy. I can use the conservation of energy technically, but if I don't have how much thermal energy was lost, then I can't, because it's a inelastic collision does not conserve mechanical energy. And finally, we talked about the opposite of a hit and stick, essentially, and that is an explosion. And that is where the objects start at rest, or they could be moving to the right. Doesn't actually matter. And if I have two objects, they go off in equal and opposite momentums in equal and opposite directions. So there's a momentum going in this direction and momentum going in this direction. And if pi is 0, then pf has to equal 0 as well. So an explosion, now again, I just said that it could be already moving to the right, and then it's exploding and moving faster to the right and to the left, but the initial momentum still has to equal the final momentum. That's the big concept. So with conservation of momentum, we can use this to analyze the different types of collisions. And I'm going to quickly go through each type. So with an elastic collision, let's say that two objects are moving towards one another. So I have cart 1, and that's moving towards cart 2. Now, and cart 2 is moving towards cart 1. So we'll call this guy 1 and this guy 2. So there's initial momentum for 1, there's initial momentum for 2. And the cool thing is, these two, we're going to assume a perfectly elastic collision, which means these two carts are going to hit and bounce. What's interesting is that cart 2 is going to transfer its momentum to cart 1. Cart 1 is going to transfer its momentum to cart 2. And after the collision, they're going to keep going. Those momentums are going to keep going as if nothing ever happened. And we did a huge lab on this. We did the collisions lab with this to really try to visualize everything that was going on. Now, momentum is always conserved in each dimension and each direction in a collision. So with an elastic collision, the momentum is conserved. So how I quantify this is I say the mass of the cart 1 times velocity of cart 1 initial plus the mass of the cart 2 times velocity of cart 2 initial equals the mass of the cart 1 times velocity of cart 1 final plus the mass of the cart 2 times velocity of cart 2 final. So I put out this long this is essentially P1i plus P2i equals P1f plus P2f. And that's where this concept comes in. It's the sum of all the momentums. The initial momentum always has to equal the final momentum. Momentum is always conserved unless there's an impulse, just like energy is always conserved unless there's work being done. So the momentums of each of the carts have to be conserved. So in this case, it's kind of cool. The momentums, if the mass of the carts are identical, the momentums will just switch. So if cart 1 was going to the right at 3 meters per second and cart 2 was going to the left at 2 meters per second, aka negative 2 meters per second, after the collision, cart 1 is going to be moving to the left at 2 meters per second, or negative 2 meters per second, and cart 2 is going to be moving to the right at 3 meters per second. So this tells us that the momentum is going to keep going as if nothing ever happened. And that is with an elastic collision. We saw this with a variety of collisions in the lab. All right, so let's move on then. Next, we have inelastic collisions. An inelastic collision is a hit and stick. So I always talk about my favorite collision in the world, my exact, complete favorite collision in the world. Let's say this cart is moving at 2 meters per second. This cart right here, same mass, moving at 2 meters per second. All right, these two carts are moving towards one another at equal velocities and opposite directions. So cart 2 actually has a velocity of negative 2 meters per second. Now, in inelastic collision, momentum still has to be conserved. So I have the mass of cart 1, velocity of cart 1 initial, plus the mass of cart 2, velocity of cart 2 initial. And these two hit and stick. And as Schaefer likes to say, two masses become one, or whatever he does, some weird biology thing with it. So these two add together, and then they have a shared common final velocity. So an inelastic is a hit and stick. They have a shared common final velocity. So here is my inelastic collision equation. Now, this again comes from the mass of the cart 1, or momentum cart 1 initial plus momentum cart 2 initial equals a shared common final momentum, aka, just like they all start, PI equals PF. Okay, so if we want to analyze my favorite collision real quick, let's go ahead and do that. So let's just call the masses mass. So then I get mass 1, velocity of cart 1 initial is 2 meters per second. Mass of cart 2, we're just going to call that mass 2. And mass 2 and mass 1 are the same, so we're actually going to cheat and call that mass 1. And then that is going to be negative 2 meters per second. Mass 1 plus mass 2 is 2 mass 1 times VF, okay? Where am I going with this? Oh, yeah. All the masses in this case do cancel. So I get 2 plus negative 2. Oh, that's going to be 0 equals 2 VF. Boom, VF equals 0. So kind of a cool collision. That is my favorite collision. These two, they collide, they hit, and they stick, and they just stop. And some of you might say, well, this violates the conservation of energy because it starts with energy and then it ends with no energy. And it doesn't. Anytime we have an inelastic collision, there is an inert loss of energy due to the rearrangement of molecules, aka thermal energy. And this is why conservation of energy doesn't work, because I could say this has kinetic energy, this has kinetic energy, and they have identical amounts of kinetic energy, because kinetic energy is 1/2 mv squared. So they have identical amounts, even though one's moving at 2 meters per second, one's moving at negative 2 meters per second. So technically, if I were to look at the conservation of energy, 1/2 mv squared plus 1/2 mv squared, I get twice the amount of energy. And that doesn't work, because instead I actually get 0 kinetic energy, as we see with an inelastic collision. Now, some of you might say, well, isn't there a way to kind of use conservation of energy and instead say that the second kinetic energy is negative or something like that? And I really don't have a good answer for you. It just doesn't work. Kinetic energy is a scalar quantity. What that means is that direction does not matter. Momentum is a vector quantity. The direction does matter, and therefore we get a better understanding about what's going on in that type of collision. So let's go ahead and take a look at our last collision. And our last collision is an explosion. Now, I'm going to start simple. I'm going to say, all right, so I have two carts. They're represented by balls or whatever, and they have plungers. And before the collision, they're together. I somehow remotely release them, and then after the collision, they are moving in opposite directions. Now, how I do this is always initial momentum equals final momentum. Now, my initial momentum is 0, which means that my final momentum also has to be 0. So if I get mass 1 and mass 2, then I have mass 1, velocity 1 final, plus mass 2, velocity 2 final. Which means that with an explosion, I have to have these masses going in opposite directions. Because again, velocity here is a vector quantity. Direction matters. So mass 2 is going in the positive direction. Mass 1 is going in the negative direction. And if you recall, the example I had with this was David and Sandra, as I remember, two ice skaters, and they push off of each other. So that's what's happening with an explosion, is it starts with 0 momentum, and it does go in equal momentum in opposite directions. And if you have more mass, you have less velocity, less mass, more velocity. Now, AP has done some stuff before where these two things are attached and moving to the right at 3 meters per second, and then they explode, and now this one's moving at question mark, and maybe it'll tell you how fast this one is moving. It's still true. Momentum initial has to equal momentum final, except now instead of 0 momentum initial, I have essentially the combined mass is my initial momentum. So I can still use the conservation of momentum to solve a problem like this. It's more complex, but I can still use it. One other thing that we talked about just a little bit, which our last little chunks here, we'll talk about angular momentum. And angular momentum was a great segue into our next unit, because our next unit is all about rotational motion. And angular momentum is essentially the momentum of rotational motion. And instead of P equals mv, I get L equals I omega. So we talk about this in the next unit, but L is angular momentum. I is the moment of inertia. And omega is the angular velocity. So in unit 5, rotational motion, we get into a ton about this I concept. And the I concept is, it's not how much mass you have, it's how your mass is distributed. And it's not how fast you're moving, it's how fast you're rotating. So angular momentum is a way of quantifying the momentum of a rotating object. It's based on the moment of inertia, I, so how my mass is distributed, and how fast I'm spinning, omega. Now, the perfect thing that we talked about with this is that if we think about like a figure skater, and this is how we can use conservation of angular momentum. A figure skater changes their moment of inertia. It changes how their mass is distributed, and that changes their angular velocity. So as the moment of inertia decreases as they bring their arms close to the center of their body, then their angular velocity increases, and angular momentum is conserved because this is a closed system. So it still follows the concept of the conservation of angular momentum. So my only question is, before, a change in momentum equals a force exerted over time. Well, how does angular momentum change then? Well, instead of P, we of course have L. We no longer have a force, but rather a torque exerted over time. And we'll talk more about torques in the next unit as well. But torque is it's not our force, it's our rotational equivalent of force. It's the perpendicular component of force times the radius away. It's what causes rotation. So we'll take a look at those two in the next segment. And with that, we pretty much, that sums up Unit 4, impulse and momentum. Momentum is just it just quantifies an object's mass and its velocity. And it comes from F equals ma. And we have an impulse momentum theorem, just like we had a work energy theorem, and that is an impulse causes an object's momentum to change. And we use this, we did talk a lot about collisions in this unit. So anytime you see collisions, a question about collisions, always go to impulse and momentum, because it's two objects interacting. And I can't use conservation of energy with collisions if they are inelastic, because I don't have enough information about thermal energy. Exactly similarly, I can't use them with explosions because it starts with zero energy, or rather it starts with potential energy, but I don't really have a way of quantifying that necessarily. So it depends on the collision. So anytime I have a collision, I will use momentum. And with conservation of momentum, we looked at different examples of collisions and how we use conservation of momentum, and we looked at angular momentum. And again, the weird thing with angular momentum is this whole concept of torque, and torque has to do with rotational motion, which we will take a look at in the next segment.